Morning, everyone. So before I introduce myself, I just want to quickly cover, what are we going to learn today? Why does it matter? And hopefully that's going to be kind of the hook to keep you engaged, okay? So we're going to be learning how can we automate the daily bottom hole flowing pressures on every well, okay? And even with different kinds of artificial lift, how can we manage that? And then we're going to say, we know that there's different pressure loss correlations out there. Which one is the best? Is there a way we can figure that out? So we're going to answer that question. For people who are on gas lift, we often have gas lift valves. And one of the questions is, what valve are we on? Are we on the top valve? Are we on the bottom valve? So we're going to look at a way that we can estimate what valve has historically been open through the well's history, all right? We'll look at how we can do this. We're going to spend a lot of time on these inflow and outflow curves, and we call them IPR, VLP. And so we're going to consider things like different tubing sizes, different flow paths, different artificial lift types, different gas lift, all these kinds of things to see what sort of rate response we can expect as we optimize our wellbore. Chokes, I'm up in Calgary, and there's a lot of people who use wellhead and even bottom hole chokes up here. So we're going to look at how can we size chokes, if we can assign different choke sizes and see what the rate's going to be. I'm just going to make sure everyone else is muted on here just a sec. Okay, looks like we are. I was hearing some sounds, but okay, so we do our choke sizing, and then we're going to do this thing called a pressure gradient calculation. And what this is really meant to do is to say, what is the flowing pressure at every location along the wellbore? And so this, we can even start to break the pressure loss between the friction and the gravity. What is the main factor that's causing the pressure loss in the wellbore? And we can even answer the question, how much pressure are we losing along the lateral length? All right, we're going to explore those things. Now, the thing I'm personally the biggest fan of that we're going to cover today is this thing called a gas lift curve. And it's just the relationship between how much gas lift we're injecting and how much the oil rate is going to increase. Okay, so it's a relationship between gas lift rate and oil rate. And we're going to figure out what is the best gas lift rate to get the highest oil rate, and where are we operating today with how much gas lift we're injecting. And that means we can start to rank and quantify the opportunity to increase our reservoir rate through a gas lift rate change. Now, there's actually a surprising amount of operators who are even over injecting gas lift, and we can look at an example of what that looks like today as well. Liquid loading, most people care about liquid loading, whether you're in gas or gas condensate. And so we're going to say, how can we look at whether the well's been liquid loaded through its whole life, and if that's something we need to worry about. Now, when it comes to liquid loading, if you've got many wells, it might make sense to make a report card. So just make a report card about which wells are liquid loaded and by how much, and that just can give you like a short list to keep an eye on. Okay, the idea of gas lift uplift screening. This is really to prioritize which wells are going to be the most responsive to a gas lift rate change, when you've got many wells, again, to find the best opportunities. Something I'm going to talk about at the very end is this idea of gas lift distribution. And this is when you have a limited supply of gas lift to share with multiple wells. And the question is, how do you best distribute that limited supply of gas lift to those wells to get the highest combined liquid rate? So this is something that's really taken off in the last year. And we even are writing a paper with Devon that's going to be presented at ERTEC about this as well. So that's just a quick preview about what we're going to cover today. And we're going to actually be spending most of our time in the software. This is not a theory course. I want to work through exercises with you today so that you can get the basics for clicking around, for doing these sensitivities, so that when you go back and look at your own wells, you can repeat the same thing, okay? So my name is Graham Helfrich. I'm up here in Calgary, Alberta, and I've been with Whitson for 3 years, and that's enough about me. Okay, so this is about a 3-hour course. like I said, we're going to be focusing on workflows in the software. If you want to learn more about the theory about bottom hole flowing pressures, about the correlations, about all the equations, in the slides that you received last night in the email from Matthias, these slides that we're looking at now, you got a copy of them. And this link is going to take you to a video that we did all about bottom hole pressure theory. So go check that out if you want to get into the nuts and bolts of that. There's this thing called the Nodal certificate, which I'll kind of show you here too. But, I want to consider today kind of like a crash course. I don't expect you to be an expert after 3 hours, but if you want to go through the same process that we're doing today, a bit slower, kind of at your own pace, you can go check out this Nodal certificate. And it's going to walk through everything we're doing today, and you can pause it. You can do little chunks and pieces here. So just consider that kind of a backup. Maybe you don't get into Whitson for a week or two after today. You might want to go check out the Nodal certificate to get a refresher, okay? And then this course is being recorded, so we'll send a copy out after as well. This is interactive, and what I mean by that is there's a chat window, okay? And we have a couple of excellent Whitson engineers who are joining us today. So if you're having any problems at all, you can type your question into the chat window, and one of them is going to help you, okay? I think we might be muted during the course, so I'm not sure if you're going to be able to ask questions, but at the very end, I'll make sure that if there's questions submitted in the chat window, we'll answer all of them, okay? And okay, one thing, just a bit of background to mention is, if you haven't used Whitson before, the thing that we're kind of the most famous for is our technical support, and we have a 2-minute response time. So when you send an email to Whitson or a support request, and I'll show you how to do that, you're going to hear from one of us within 2 minutes. Typically, you might even get 2 or 3 engineers contacting you, and then you get to pick, who has the favorite name that you want to get help from. And so the kind of questions can be anything from, hey, I'm new to the software, or where's that button, or it could be a request for some feature that you want added, or it could even be that you've done an analysis on a well, but you want someone at Whitson to just look over it with you to make sure it's looking reasonable before you kind of submit it to your manager. So these are the kinds of questions you can reach out to us. It's all included with your Whitson software. All right, so the examples we're going to do today, the first one's going to be a gas well. We're going to start kind of simple. So we're going to say, let's calculate the daily bottom hole pressures. Is the well liquid loaded? And we're going to do this thing called the flowing material balance. Now, as a production engineer, I think we probably have a lot of production engineers on the call. This is kind of diving into the reservoir engineering world, but I'm going to explain why we need to do it. And the answer is we need to know the average reservoir pressure that the well's at now. Okay, we need to do that for nodal analysis. So we're gonna touch on this flowing material balance so we can get the current average reservoir pressure. We're going to do our inflow and outflow curve. We're going to look at things like, what if we flow up the casing? What if we lower the wellhead pressure? What if we put in 2 7/8, 2 3/8? What impact does that have on the rate, on liquid loading? And then we're even going to look at some chokes. So we're going to add some chokes to this case to see what sort of rates and choke sizes we're going to get. That's going to be case number 1, starting pretty simple with gas. So the second example is going to be an oil well that's on gas lift. And we're going to say, what gas lift valve details do we need to guess what valve we're currently injecting at? What are the bottom hole flowing pressures? What's the current reservoir pressure from the flowing material balance? Do our inflow outflow curves? And we're going to ultimately try to determine, are we under injecting gas lift? Are we over injecting gas lift? What would be the ideal gas lift rate on this well to get them the highest oil rate? All right. So those are kind of the main cases that we're going to work on today. I'm also going to preview kind of what are we working on, what's coming around the corner for your Whitson software, and that'll be at the very end. Okay, so we're going to start with the gas well, but I want to make sure everyone can log in. So we're all going to go to courses.whitson.com right now. And I'll give everyone a minute to do that. So courses.whitson.com. When you get there, the email you're going to put in is the email that you registered for this course with. Okay, and I've got the password down below. It's Nodal 123 exclamation mark. So again, the email is the email that you registered for the course with. Maybe as people successfully get logged in, go ahead and try to give a thumbs up in the Teams chat window there. I'll show you where that is. It's under React. Thumbs up. Okay, I got a thumbs up from Trevor, Mohammed there. Okay, and again, if you're having any trouble logging in, I want you to write something in the Teams chat. The chat button is up at the top here. It says chat. So if you're having any trouble, go ahead and ask a question there. So email is what you registered for the course here. Password is down here, Nodal 123 exclamation mark. I'm gonna give people a few minutes to log in just because I don't want to leave anyone behind. Okay. Now just to I'm gonna go ahead to the chat when I'm gonna enter the oh good. Thank you for putting the password in there, guys. So just FYI, everyone has Whitson access now through courses. You know, if you work at a operator, you're typically going to go to, for example, you know, shell.whitson.com or chevron.whitson.com or, you know, any of these, you know, devon.whitson.com. If you're not sure what your company's Whitson domain is, you can reach out to me after the course. I'll get you pointed in the right direction. For most companies, you don't need a password. We've got this thing called single sign-on. So the same security that you use to access your work email through the web, it's the same thing that you would log into your software with. And but you know, this course's access will last for a couple of days, so it's just temporary for the training course. All right, that's how we're accessing it today. All right, so I think everyone should be logged in by now. And what we should be seeing is something like this. Okay, it should be looking something like this, where we got this this picture. We've got these kind of little boxes on the left side. Okay. Now the general workflow is on the left side. We kind of go top to bottom. The first three rows, fields, projects, wells. These are just ways to organize your wells, and I'll explain that in a second. As we start analyzing a well, first we're going to do our PVT, look at the production data. A lot of these steps on the left side, these are for people who care about declines, who care about rate transient analysis. For us, we're really going to be focusing on the nodal workflow today. So we're just going to pick and choose a couple of these steps on the left, really only one or two. But the general workflow is top to bottom. So today we're going to do PVT, bottomhole pressures, flow material balance, and nodal analysis. And that's pretty much it. We're going to stick to those steps, and that's what we're going to do today. So what I want everyone to do is to click on this field here that's called Nodal Course March 2026. We can click on that, okay? Now, once you're in there, you should see two of these so-called projects. So we just went from the top kind of tier, which is called a field, and that is typically like a geographical area somewhere in the world, or like you have the Permian field and the Bakken field and the DJ field and the Eagleford field. So that's how fields are organized. Now we're one level down in a field called a project. And a project is typically just a group of wells. So here we see that, oh, there's no wells in here. That's weird. Let me refresh it. Oh, they are. Okay, I just needed to refresh it. No problem. So we see that I've got a couple projects in here, and one of them has 27 wells. The other one has 2 wells. So the reason you would have a project is really just like a folder. So imagine that you've got like hourly flowback data. You might put all of your wells with hourly flowback data in one of these projects. And then another project might be your daily production data. And then another project might be monthly, like non-op data. So that's typically a reason people will organize or have multiple projects. We have lots of operators who have over, there's 30,000 wells in one project. So just to give you a sense of scale, okay? Now the project we're going to work on is one called main. So I want everyone to click on the word main. Anywhere along this row is fine. Just click on main. We should see two wells in here, oil well and gas well. And we're going to start with the gas well. So we can all click on the row called gas well. All right. So I want everyone to go over to the left side where it says PVT. PVT. Now, there's a bit of a catch here. So Whitson is a multi-user software, meaning that everyone on the call, we're actually looking at the exact same well right now. And what that means is if Mohammed or Julia or Scott go ahead and change this well or change an interpretation, I could go in and screw it up for them, right? So that's the problem with all of us looking at the exact same well. And the way we get over that is we have something at the top called scenarios, right? So it says scenarios main. What I want everyone to do is under scenarios, click on it and say add new scenario right there. And what I'm going to call it Graham H. We've got a lot of people on the call, so maybe put your first and last name or your 3 initials, something that'll be kind of unique to you, okay? Now, a scenario, it's really just like a sandbox that you can do whatever you want it, right? And as you can see, that your scenario can either be company-wide, which means everyone else can see it, or if you're feeling a little bit shy, you can make your scenario private. And that means you're the only one who can see that it even exists. All right. You can change the status of this later, but for now, it doesn't matter if you make it private or company-wide, pick whatever you want. So as long as you've entered your name, go ahead and click save. Okay. So I'll probably see now that there's lots of people who are starting to make your own scenario. That's awesome. We've got our own little sandbox, but we're looking at the same well under our scenario. So things that can be unique for your scenario is the PVT, the bottom hole pressure correlation that you're using. Anything you do in your nodal analysis is unique to your scenario. There's only one thing that is common among all the scenarios, and that's the production history of the well. So the daily rates, the daily surface pressures, those are going to be common among everyone's scenario, but that's it. Everything else can be unique to your scenario. Okay, so a bit of background. So other companies I've worked at or other engineering software I've used, when it comes to PVT, they typically use correlations when it comes to viscosity, compressibility. But you may or may not know, but Whitson, the company Whitson's been around for more than 30 years. And for the most of that time, it's been focused doing PVT consulting all around the world. We're kind of famous for being PVT experts. I'm not personally, but thankfully there are people, everyone else at Whitson is a PVT expert. And so for that reason, there's actually an equation of state model built right into Whitson. And when I first heard that, I kind of got a bit scared because I don't really know what an equation of state model is or why I care about it. But I want to show you that it's actually very easy to use and why it's going to matter for you, okay? So we're under PVT. We've got this little reservoir fluid composition box up here. And in the corner, we've got a little square box, and we want to click on this square box right here. Okay? Right here. All right. So this gas well that we're looking at, it happens to be dry gas. Okay? There's no condensate, there's no oil. And for that reason, we've got a specific gravity entered of 0.6. All right. Now, later, when we look at the oil well, which will be next, or if you guys have gas condensate, instead of putting the specific gravity in, we're actually going to look at the well's initial GOR or CGR. And it's going to be a bit more exciting because this is a dry gas well. We're not really flexing the muscle of the equation of state model, but I'll explain in the oil example how it works a little bit more, okay? So here we've got our specific gravity plugged in, our initial reservoir pressure, and our reservoir temperature, all right? So we can click save down on the bottom right. Okay, now normally if we had an oil or gas condensate well, we'd see this really beautiful phase envelope being created for us automatically. This gas is a little bit too dry to have that, so we're not seeing that. But for the oil example, it's going to be front and center, okay? All right, so PVT is done. Again, if you missed that step, under PVT, click on the little square box, and then click Save, and that's it. Okay, so that's the PVT step. Let's go to the left. We're going to go one step down called Production Data. So this is the well's daily rate and surface pressure history. This well's about 2 years old, and we can see that the gas rate in red, initially it was 30 million cubic feet a day, and the rate was pretty flat for a while. And now the rate has gone down to around 6 or 7 million cubic feet per day. There's a dashed gray line, and that's our surface casing pressure. This well actually has no tubing installed. They've been flowing up the casing with no tubing, and that's why we only have casing pressure. There's no tubing pressure because there's no tubing in the well. And of course, we have our water rate. Now, the black line is interesting. This is actually a gauge pressure. Now, most people don't have downhole gauges, but I'm going to show you, if you happen to have a downhole gauge, how you can use that to kind of calibrate the bottom hole flowing pressure and the correlations. So again, I know that not every well has a downhole gauge. This one happens to have it, so I'll show you how we could leverage that if we need. Let's explain how to manage some of these plots a little bit. So we have this legend in the top, and if we click on the word gas in the legend, you'll notice that it toggles gas off or toggles it back on. We can do the same with water. Toggle it off, toggle it on, casing pressure, toggle it off, toggle it on. Okay, so that's one way to use the legend. Now, what if I only want to show the gas rate? There's a shortcut. So up in the legend, we go to the word gas, and we're actually going to double click on the word gas. And that will cause only that fluid to be shown. If it didn't work for you, it means you need to double click quicker. Okay, so I'm going to try double clicking on water. Okay, and that causes only water to be shown. So single click is to toggle something on and off, and double click is to show only that fluid. Okay, so I've got everything but turned back on. Let's talk about zooming for a second. So my favorite way to zoom is to drag, I'm going to hold my mouse button down, and I'm going to draw a box over some of the data like that. So what I'm doing is I'm just dragging and drawing a box over some of the data, and when I let go, it's going to zoom in to that part of the data. And you can even do it again. You can draw another box, zoom in, you can do it as many times as you want. But if you're like me, eventually you might accidentally zoom in to something where there's nothing, and you're like, okay, where did all my data go? How do I kind of reset my zoom? So to do that, all we have to do is double click anywhere in the screen, like in this plot. Just double click anywhere within the plot, and that is going to reset your zoom. So let's try it again. Let's zoom in on some data. I'm going to zoom in on the water this time. Zoom in, draw a box, and then I can double click within the plot. It's going to reset the zoom. Now, if you're not a fan of double clicking, there's also a reset zoom button up in the top right here, and that does the same thing as double clicking. That'll do the same thing. One thing to notice is down on the x-axis, the time is in cumulative time, right? 100, 200, 300 days. But if you prefer like a calendar date format, if you notice up in the top left of the plot, it says the words dates, okay? Dates right there. So if you click on that, it's going to change things to calendar time. So that might be a bit more useful for you, depending if you like dates or cumulative time. All right. Let's talk about units for a second. I know I'm using these field, kind of American units, but up at the very top, there's a button that says F, or change unit system right here. Okay, so we've got, right now we're in like PSI, barrels, millions. If we were to do SI metric, that's going to be, you know, cubes and bar. I don't know too many people who use bar. These Canadian ones, this is going to be kPa and cubic meters. And then for our Calgary friends are a bit unique because they like mixed units. They like pressures in kPa and they like volumes in millions and barrels. So we have this special Calgary unit, and then we even have some Argentinian friends where we use kilogram per centimeter cubed or squared, and cubic cubes for the volume. So if there's some unit system missing that you guys like that we don't have here, just let us know. I'm going to go back into field units for the course today, okay? I'm a barrels and millions and PSI guy personally. All right. Now, one last thing before we kind of leave this production data plot is this idea of comments. So up in the top right, you'll find a box that looks like a little voice bubble right here. Okay. Now, what this is for is if there's been any sort of event, like an offset frac hit, a choke change, a compressor issue, any sort of event that you want to make a note about to visualize on the plot. So if you click on this little production comments button on the top right, okay, you can say add comment. Okay, and then wherever you go, like I'm going to go to the production data. You can go anywhere you want on the plot, but just click on some place along the production history, okay? And for me, I'm going to write choke change, or you could write whatever you want, offset frac hit, you know, refrac, anything you want, and then you'll click save. So it's basically making a note of that event right there. And that note will kind of persist through other places in your analysis as we continue. You know, you're probably imagining, but the reason we did that is if we see some sort of change in the well's productivity, then we might want to wonder why, right? But if we have some comment about that there was a refrac, there was an offset frac hit, there was a tubing change, now we can start to connect the story together. So these comments, you can either manually add them like this, or if you have them in a table with the time associated with it, you can also bulk import them and automate them and bring them in that way, okay? Great. So the reason I wanted to spend a time on the legend, on the zooming, is because these controls are true for everywhere we're going to work in the software. Okay, one last thing for zooming. If we go down to the very bottom right corner of the plot, down here, you're going to find when you get your mouse in just the right place, it's going to turn into a double-headed arrow. So I'm down in the bottom right, and I've got this double-headed arrow. You kind of, if you don't see the double-headed arrow, you just have to kind of move it around till you get it in the right place. Once you see that, you can hold your button down on your mouse and you can drag left like that. And when you let go, it's going to stay there. You could even do it again if you want. Bottom right, click, drag like that. And if you go up to the top left corner, we can do the same thing. So I move my mouse till I get that double-headed arrow. I'm going to click and drag down. Click and drag down. Okay. And if I want to zoom back to my kind of reset my zoom, I just double click in the plot and it resets my zoom. All right, that's it for kind of controlling our zooms. Let's calculate the bottom hole pressure for this well. So on the left side, it says bottom hole pressure. We'll go there. All right, so we've got this pump jack picture. And up to the top right of that, we have the little square box, and we're going to click on that square box right here. So the first thing we see is the deviation survey. So we have MD and TVD. And if you want a kind of a visual preview of the well bore, there's a little blue icon above the table. It looks like a curve, right? If we click on that, it's going to show us a visual of what that deviation survey looks like. Okay, we can close that pop-up. Now, by the way, if you're saying, if you're saying, how do you get the wellbore description in here? Typically, if someone has like WellView, or if you have your wellbore details in any sort of database, we will connect to that either using like an API connection or Snowflake or Databricks. The whole point of this is that your wellbores and your production data, you don't want to have to do some Excel import. It's all usually automated and brought in automatically that way. And if it's not, if you find that you have to, can everyone make sure they're muted? Thank you.
Yeah,
yeah. So next what we're going to do is go up to the top right where it says well data up here. So this is where we have our tubing description. What's our casing size? What's our tubing size? What kind of artificial lift are we using? Now this particular gas well has the most simple wellbore you can imagine. We're just flowing up the casing, right? There's no tubing, there's no artificial lift. So again, this is the most simple kind of wellbore because we just want to get started a little bit easy, right? So we've got our casing diameter here, our size and all that. So we use this to calculate the bottom hole flowing pressures. Now I mentioned that this particular well happens to have a downhole gauge in the well, and I know not every well will, but when we have a downhole gauge, it's important that we mention the depth of the gauge, okay? Because we want to know what that reference point is in terms of its depth so we can compare it to the calculated bottom hole pressures using correlations, okay? So if you ever have a downhole gauge, this is where you would put the gauge depth, just for a reference. All right, we're ready to calculate the bottom hole pressures. Let's close this well data screen. And we're going to go in the very top left and click this big blue button, calculate bottom hole pressures. Now, everyone should be seeing a plot that looks like mine where there's a few different colors down here. So what these colors are, these are the daily calculated bottom hole flowing pressures for this well. So we took the casing pressure. I turned casing on up in the legend. We took the daily casing pressures, we took the rates, we took the wellbore description, and we converted that casing pressure to bottom hole flowing pressures for the well. And the reason that there are a few different colors is because there's different pressure loss correlations available to calculate the bottom hole pressure. Beggs and Brill, gray, Hagedorn and Brown. You're probably familiar with all of those ones. The one you might have never heard about before is this green one, and you can either call it the green one, you can call it W and G, or it's Woldesmahat and Gahar. So the reason these correlations have different results is they all handle liquid holdup a little bit differently, okay? Now, these results are actually pretty close to each other, but as you get more water, as you get more oil, the results are going to start to separate a little bit farther apart. But in this case, we have gas with just a little bit of water, and that's why the results are all pretty close to each other. So you're thinking, okay, which correlation do I use? So, I was taught that gray is good for gas wells, Hagedorn and Brown is good for oil wells, and Beggs and Brill is good for wells with water, watering and hydrocarbons. So is that true? Well, 2 years ago, we did a study to answer that question. And I'll send you guys the paper out in the follow-up. So we received permanent downhole gauge data for over 600 wells. So some of our partnered operators here gave us the downhole gauge data, and we used that to compare the bottom hole pressures through a correlation, right? So we have the measured bottom hole pressures, and we're going to ask ourselves which correlation best matches the measured bottom hole pressure, right? There's nothing better than a measurement, right? So I'll just skip forward to these results here. Again, I'll send you guys the paper if you want to go through it. It's a pretty easy read as far as papers go. But because the wells that we received were from a huge range of reservoirs, Eagle Ford, Permian, Montney, lots of different reservoirs. And for that reason, some of the wells had very low GORs, and some of the wells had very high GORs. And we bucketed all these data points by GOR to see, does GOR have an impact on how good the pressure loss correlation is? So if Beggs and Brill perfectly matched the downhole gauge pressure, then all of these blue dots would be at 0%. But in fact, Beggs and Brill over-predicted the bottom hole pressures by 16%, quite a bit. Gray had the opposite problem. It under-predicted the bottom hole pressures by about 12%, even with really gassy wells. So I was surprised at that because I thought Gray was the cat's pajamas for gassy wells, but in fact it under-predicted the bottom hole pressure. Hagedorn and Brown was pretty good. It was within about 5% of the gauge pressure. And then this green one, Waldesman-Gahar, was also within about 5% of the gauge pressure. So this is when we bucket by GOR. But there's kind of a weakness of GOR, and that is that it ignores water, right? Water is not in the term GOR. So we did the exact same thing, but now we bucketed by gas liquid ratio, so we could account for the water. And the results were pretty similar. The only difference is that Hagedorn and Brown seemed to get worse as the gas liquid ratio got higher, where the green one, Waldesman-Gahar, it stayed pretty constant at about 5% error all the time. And so at least from this study, I personally use the Waldesman-Gahar bottom hole pressure loss correlation if I don't have any downhole gauge data. So that's kind of my new default correlation, my new favorite, okay? All right, so back into Whitson, we need to pick one of these bottom hole pressure loss correlations to use and move forward with our analysis. So up at the very, very top here, kind of beside the pump jack, it says bottom hole pressure to be used in calculations. And we're going to click on that, and we're going to pick the one called Waldesman-Gahar right here. This is our new favorite bottom hole pressure loss correlation. So that's the one that we're picking, we're committing to it, and we're going to be using it for analyzing this well now. Now, I forgot one thing. We have a gauge pressure on this well, okay? So the gauge pressure is, it's kind of hidden in these lines. It's the black line. So that's our measured bottom hole pressure. And so what I may want to do is use that gauge pressure to tune or modify one of these correlations to make the correlation even better, right? To match the correlation against the gauge pressure. So if that's something you want to do, we're going to go up to the very, very top right. There's a button that says tuning. So we're going to click on the word tuning up here. And the correlation we want to modify is our Waldesman-Gahar. So we're going to go way over to the right and click on the word tune. You're going to get a little pop-up and you're going to say yes. So what this is doing is it's automatically changing the liquid holdup and the friction factors in the correlation to match it against the gauge pressure. And if you want to visualize how that match is working, down at the bottom here it says show fit. So we can click on show fit. Okay. And so black is our gauge pressure. Green is the bottom hole pressure loss correlation after it's been tuned. So it's basically like a history match of the correlation against the gauge pressure. Okay, I'm going to, let's see. I'm going to close this little pop-up here. So I'm going to say save. Okay, save is going to save those tuning parameters that we just did. And I have to recalculate. So the very top left, calculate bottom hole pressure right here. That's going to update the bottom hole pressures for that tuned correlation. So now we have a custom bottom hole pressure loss correlation that's kind of better than the default one. And part of the way people will use this is if they have other wells that don't have a downhole gauge, you might start with this default correlation, but you can actually go ahead and apply those tuning parameters to all your other wells that you think are analogous to it. So this is just one of the cool ways to make your bottom hole pressures even more reliable and take advantage of any gauge pressures that you might have downhole, okay? All right, So let's talk about IPR curves for a second. Okay, so did anyone still have a car with 3 pedals on the floor? I find it's more rare to have a manual transmission these days, right? But what happens is when you push um, this throttle down, what you're really doing is there's a cable attached to that, and it's opening up this valve, which is called the throttle body. Or if you have an old car, it's a carburetor. And so when you open this up, it's letting more air into the motor. All right, so that's what happens as you put your foot on the pedal. And so we can actually build a relationship between the position of our foot and how much horsepower the motor's making. And so it's kind of like this. If we're just idling in our car, right, we don't have our foot, we have it completely off the pedal, we're not making any horsepower, right? But as we start to push our foot down, down, down on the throttle, we're making more horsepower. So WOT means wide open throttle, and that's when we're making our maximum horsepower. So those are the kind of two extremes, right? Idling, or we have our foot floored. But in fact, we could be at part throttle, right? Or we could be pushing the throttle halfway down, and we'd be making some horsepower. And so this line is really just a relationship between our throttle position and the horsepower the motor's making. Now, this is very similar to an IPR curve, but instead of our throttle position, we talk about drawdown, okay, versus the rate that the well will produce. And so if the well is shut in, we have 0 drawdown, and the rate is 0, right? That's shut in. The opposite of that is if we're at our maximum drawdown, then we're going to have our absolute open flow rate. That's the highest rate the well can produce. But in reality, we're usually operating somewhere in between these two extremes, right? But this line is that relationship of drawdown versus what the rate of the well will be, okay? Now, we don't always talk about in terms of drawdown. We might talk in terms of what is the flowing bottom hole pressure. And when I say flowing bottom hole pressure, I mean, what is the pressure down here kind of at the perforations, right, in the wellbore? We might have a very high reservoir pressure out here, but it's the lower pressure down here in the perforations that's causing a delta P across the sand face, and it's that delta P that's causing flow to happen, right? So the higher the pressure differential across the sand face, the higher the rate's going to be. So again, if we're shut in, we have no rate. If we have very, very low bottom hole pressure, we have the highest rate possible. And so this is our IPR curve. It's really the bottom hole flowing pressure related to what the rate will be from the well, okay? Now for a gas well, we use this equation. It's called the back pressure equation. It's called the C and N equation. It's called the Rollins-Schellenhardt equation. But this is one of the ways we create this curve for gas wells. So this is the gas rate that we're typically trying to solve for. C, you can think about this kind of like the well's productivity. And this is the reservoir pressure. Now it's important, this is not the initial reservoir pressure. If this well is 2 years old, we've depleted some of the pressure. So we don't put the initial reservoir pressure, we want to put in the current reservoir pressure. I'm going to talk about how we can get that. So current reservoir pressure and the bottom hole flowing pressure. So what's within these brackets is the delta P. It's basically the drawdown of the well. N is this turbulence factor, and we typically don't really know what it is, so we just assume 1, typically, okay? So how do we take a well that's producing and create the IPR with this equation? So let's pretend the well's producing, okay? The current average reservoir pressure is 2,000 pounds. Okay, we plug that in. The rate that the well's producing is 150,000 scuffs a day. Okay, we plug that in, that's our current rate. And the current bottom hole flowing pressure is 1,200 pounds. We plug that in. Okay, we assume that N equals 1, and guess what? We only have one thing to solve for, and it's the C value. So once you have put in the current average reservoir pressure, the current rate, the current bottom hole flowing pressure, you can create this curve. You're basically drawing a line through this point, and that's your gas IPR curve. Okay, now for wells that are higher pressure, we happen to use a pseudo pressure in the back end of Whitson. It's just a little bit more correct. And so that is it for IPR. So let's go ahead and answer the first piece of the puzzle, which is what is our current reservoir pressure? Okay, we know that we need that for the IPR. So on the left side, we're going to go to something called the flowing material balance. Flowing material balance on the left side. When we get there, we're going to click this blue button that says run. And we should all see something that looks kind of like this. So the job of the flow material balance is to tell us how big is the reservoir? How big is the tank that we're draining from? And to do that without a shut-in. So our daily rates, our daily bottom hole flowing pressures that we've calculated are all being plotted on here in this very fancy way. So this technique was developed by Coterra, and it works in gas wells, oil wells, gas condensate. Even if you're below the bubble point, it's still good. So what I want us to all do is take this black line, we're going to move it. So if you go to the middle of the black line, you can drag it around like this. But if you grab the tips of the black line, you can change the slope. And what we want to do is we want to try to find the most shallow slope that we can observe for this well. So I'm going to give everyone a second to try to get a slope that looks kind of like that. And again, you can grab the tips of the line to change the slope. Okay, so if everyone kind of has a interpretation there, I want us to look up here. So there's a number, it says contacted OGIP, original gas in place. And I'm around 22 BCF. So again, the job of the flow material balance is to tell us what is the contacted gas in place, or how big is the reservoir, or in an oil well, what's the oil in place? And it's doing that without a shut-in. So again, this is all flowing pressure data from the well. Now it's really the slope of this line that dictates how big the reservoir is. If you were to grab the tip of this black line and move it up, so a steeper slope, and then you let go, that means we have a smaller reservoir. We have a smaller tank, only 6 BCF. If we have another well that has a more shallow slope, that means a bigger reservoir, 75 BCF gas in place. So this original gas in place, it has nothing to do with EUR or recovery. This is truly how big is the reservoir. It doesn't tell us how much we're going to get out. It just tells us the size of the tank. So just so that we're all on the same page, I want us to click on this autofit button in the top left, autofit, okay? So there's two options. One says standard autofit, and the other says make sure that the average reservoir pressure is above the flowing pressure. I'm going to pick the second one, okay? I'm going to wait till the oil example after this to explain why we have these two options, but for now, I want us to pick this second option under autofit, okay? Okay, so I'm getting about 20.9 BCF. You guys should be something similar. Okay, I'm just gonna have a quick preview over here. You know what? Because I have a little bit of experience analyzing these wells with the flow material balance, I think that number might be a little bit small. So what I want to do is change my slope so that I'm around anywhere between 22 and 23 BCF. So again, what I'm doing is I'm changing this slope, and I'm watching this original gas in place number. So I want it to be between 22 and 23 BCF. I want everyone to do the same, okay? Okay, so if you've changed your slope, again, the tips of the black line, and you're between 22 and 23 BCF, I want you to click that run button one last time in the top left. Okay, that's just going to update everything for us. So you're saying, Graham, what does this have to do with production engineering? Where's my average reservoir pressure? Okay, the answer is in the top right. So we have this plot called pressure way up in the top right, and I want to expand that. So there's a 4 arrow box like that. We're going to click on this to expand this pressure plot. Okay, so we have a black line. Can everyone make sure they're muted, please? Thank you. Okay, so we've got a black line and a gray line. The gray line, these are the bottom hole flowing pressures, right? We took our casing pressure, we calculated them down to bottom hole flowing pressure. So that's what the gray line is, flowing pressure. The black line is average reservoir pressure. So back when this well was brand new, the initial reservoir pressure was around 4,400 PSI. But as we produced and we depleted the well, we're able to estimate how our average reservoir pressure is getting lower and lower. And the way we're doing that is we're using the slope. Remember the slope of the line we just did? That's estimating how big the tank is to begin with, 22 BCF. And because we know how much gas we've cumed through the well's history, we use material balance to figure out what reservoir pressure is remaining. And that's where the black line is. So today, we're around 1,600 pounds average reservoir pressure. You guys should have a number that's pretty similar. So the end of the black line should be around 1,600 PSI. Now, if we remember, what do we need current average reservoir pressure for? We need it for the IPR curve, and that's the number we're going to use. Okay, good. Finally, we can go down to the left side and click on Nodal Analysis. Nodal Analysis down here in the bottom left. All right, so when you come in here, you should be seeing a red line and a black line. Now, for me, the scale is a little bit funky here. So what I want to do is go to the top left so I see that double-headed arrow pointing up and down. So the top left of the plot, I'm going to see that double-headed arrow. I'm going to click down and drag this up so I can see the IPR a little bit better like that, okay?
Graham, can you just quickly go to the FMB? I think some people just like do a 1-minute summary of the steps of FMB.
Absolutely.
Some people were having issues with the data
you
loading and stuff. Yeah,
absolutely. So when you come in, yeah, you bet. So when you come into FMB, the first thing you need to do is going to click Run up here. Okay, and what we're going to do is we're going to try to move this black line, and I'm going to grab the tips of the black line because I want to try to make the black line match the most shallow slope that I can find along these blue dots, which is your daily rates and pressures plotted in a fancy way. And I'm going to move this black line around until this number here, which says contacted OGIP, when it's between 22 and 23 BCF, that's about what I'm looking for. So after you've got a slope that you're happy with, you're going to click Run in the top left one more time. And that is going to update this plot in the top right, which is called pressure. And it's this black line that is our average reservoir pressure that we're predicting. And the very end of the black line should be around 1,700 PSI, something like that. If anyone else is having trouble with that, and let me just mention something real quick. If you need help from the Whitson people in the chat window, what you can do is you can grab this URL, so the link at the very top. If you were to copy that and paste it into the chat window for one of the Whitson people, they can click on it and see your well. Okay, just an FYI. This is actually a good moment just to explain how do you actually reach out to us for support. So there's two ways. If you want to email us, it's support@whitson.com. But kind of the easier way is you're going to find there's a little voice bubble up in the top right of the software right here. Okay, and if you click on that, you can say, call me now, right now. And if you're being really nice, you can say please. You don't have to say please. But once you click save, everyone at Whitson is going to get an email, and we're going to get a link to your well, and not only to your well, we're going to get a link to the exact page you're on. Okay, and so you're going to hear from us within 2 minutes, and we can get on a call. We can see what you're seeing. Okay, so that's just a quick tip for the support. Okay, so down to nodal analysis on the bottom left, nodal analysis. We should see this red line, this black line, and I kind of adjusted my scale by putting my mouse in the top left of the plot like this, so I see a double-headed arrow. You've got to move it around to the right place so you see the double-headed arrow. I'm clicking and I'm dragging up to kind of fill up the plot a little bit better like that. So what are we looking at here? Well, the red line is the IPR curve. And you'll notice where the IPR curve intersects on the y-axis, it says about 1700 PSI. And that's the same number here. Well, where do we get that from? That's our average reservoir pressure. We got that from the previous step, from the flow material balance. So it's automatically using the flow material balance average reservoir pressure when we create the IPR curve. Great. What's the black dot? So the black dot is the most recent day of the well's production history. So the most recent rate, 7 million cubic feet a day, and the most recent bottom hole pressure, about 1,200 pounds. So it's using the most recent rate, kind of like a sample drawdown, to help give it this dot, and we have this point. So we just need 2 points to create the IPR. We need the average reservoir pressure, we need the current operating conditions, and that creates the entire IPR curve. Okay. The black line is called the VLP curve, or you might call it the tubing performance curve. And this is really the tubing hydraulics at the current conditions to show how the tubing hydraulics match with the reservoir productivity. And wherever they oversect, that's the well's operating condition. So you know what, I totally forgot liquid loading. Okay, we're going to go back up to the left side where it says bottom hole pressure. Okay, bottom hole pressure. Up here. On the left side, bottom hole pressure. And under the pump jack, it says liquid loading plot. We'll click on that. All right, so just a bit of background, liquid loading is really when the velocity of the gas is not high enough to carry the water up to the surface. Okay. Ideally, we want the velocity at the end of tubing or the perforations to be high enough to be going fast enough to drag the water up all the way to the top. Once we drop below that velocity, the water will drop down in the wellbore and start to pool up and usually cause some slugging or some rate loss. Okay. So the red line is the well's actual gas rate that it produced historically. And the blue line is the minimum rate that we need to avoid liquid loading. So we want our actual gas rate to be above the blue line in order to avoid liquid loading. Now we happen to be using the Turner velocity, which is a way to calculate liquid loading. There's also a Coleman, which is just 20% different. And there's these other ones called Nagu and Belfroid, but I like to stick with Turner or Coleman personally. So this well is not liquid loaded because the red line is above the blue line, but more recently, it looks like there might be some slugging going on and we're kind of getting under that blue line. So there might be some liquid loading going on in the well now. If you ever, let's say you've tried Turner, you've tried Coleman, they don't quite match with your field observations about when liquid loading happens, you can modify them. So there's this little blue droplet here above the plot.
Graham?
Yes.
Yes, can you hear me?
Yes.
Okay. Good morning here, Gustavo.
Hi.
From Argentina again.
Yes.
Nice to hear you again.
You
Yeah, this critical rate that you are showing here is
Yeah.
associated with the tubing. That case, can you plot both casing and tubing at the same time?
not at the same time. So in this particular well, we don't actually have tubing in the well. They're only flowing up the casing. So, but I agree what you're saying. Like if the well had tubing in the well, then what we would be showing is we would be showing the minimum rate at the end of tubing. That is what is
Okay.
shown.
Okay.
That's what's shown when there's tubing installed. But if you want to also report the liquid loading rate down in the casing, typically at the top perforations, you can change to report at that depth. But at the moment, you have to pick one at a time. So at the moment, we can't show both, but I think that would be a good idea. Like in the same way that you can turn Turner and Coleman on at the same time, I think we should allow the option to turn on different locations at the same time. I think that's a good request.
Okay. Okay.
Yeah. Yeah.
In some cases, we started with the casing production, and after that,
Yeah.
maybe a year,
Yes.
we changed to tubing. So
Yeah.
maybe have the both cases should be good.
Okay. So
Yeah.
for that question, the answer is yes, we can do that. So you guys don't have to follow me. I'm just going to show you this. So if the wellbore has changed flow paths during
Okay.
its history, like let's say you went from casing to tubing, then you went on plunger lift, then you went on gas lift, you can basically hit this little plus symbol, and this will let you add a date whenever something changed in the wellbore, right? Going from casing to tubing. And so when you have that archive of flow paths with dates, then the critical rate in blue will update and reflect the minimum rate through time, depending on
Oh,
what the flow path is. Yeah, so that happens now.
okay.
Yeah.
Okay, that's clear. Thank you.
Perfect. Okay, so this little blue water droplet right here, if you click on it, you have the option to modify Turner or Coleman. So if you typed in 1.2, it would raise it by 20%. Or if you put in 0.8, it would lower it by 20%. So again, this is just for people who have field observations of liquid loading that don't match Turner, but you can modify Turner to reflect what's happening in the field. Okay. So I'm going to say let's keep it at 1 for now. We don't want to change it. If you change it, turn it back to 1, so we're all on the same page. Okay. Okay. The last thing on this plot has to do with erosional velocity. If your gas velocities are very, very high, typically at the wellhead, like at the top of the tubing, you can start to erode your tubing. And so if you're wondering, am I getting close to that erosional velocity? There's a drop down here that says erosional rate type. Okay. If we click on the one that says API 14E right here, we get a purple line. So this is the rate that we need to start worrying about erosion at the top of the tubing. Now, in this case, we don't have to worry about it because our actual rate in red is below the erosional rate. But if you ever saw your rate above the purple line, it would tell you that you should be worried about erosion. The nice thing about API 14E is you don't need details about the sand. If you pick the other options, Feedman, you need to put in a little bit of sand detail. That's the difference between these two methods. Okay. Okay, so the takeaway from this is the well may be very close to liquid loading. Okay. I apologize. I should have covered that earlier. Let's go back down to nodal analysis down on the bottom left. So the black line, our VLP curve, part of it is solid and part of it is dashed. So what that means is the dashed part means we're below the Turner velocity, meaning the well is liquid loaded if we're operating on the dashed part. But if we're operating on the solid part of the black line, it means we're above the critical lift rate. But I can see that we're very close, like we're almost liquid loaded, and that's consistent with the previous plot that we just looked at, right? So it may be time to lower the wellhead pressure or to put some tubing in the well to delay liquid loading, okay? So we're going to wrap this gas example up and then we'll have a break, okay? So I want to talk about one thing quickly before we talk about different tubing scenarios, and that has to do with this sample point in the black line, right? This is the most recent day of rate and bottom hole flowing pressure. But often if your well is kind of going up and down, you might not pick a good rate. You might pick a rate that's not representative. It's too high, it's too low, and that can impact the shape of the IPR curve. Okay, and what I mean by that is I want us to all go in the left here. You'll see a picture of a calendar icon right here, okay, this calendar icon. We can click on that. And you'll notice that there's a dashed black line at the very end. So this is the day that's being sampled for the drawdown, for the IPR. But if you were to move this to a different point, maybe where the rate is low, right? A day where the rate is low, and you were to click save, it's going to calculate a new IPR, and it's a much lower IPR curve than we had before. So I just wanted to show you the risk of picking maybe a non-typical day of production. It can affect the shape of your IPR curve. So one of the ways we can actually solve that is above the plot, you're going to see 3 little blue dots up here, okay? See those 3 little blue dots? If we click on that, we're going to pick show points. Okay, and your dots may look a little bit different depending which day you picked. But what these points are is we're actually looking at 10 days. So we're taking 10 days around the date that we kind of picked. So 5 days before, 5 days after, and it's showing us what the rate and bottom of flowing pressure was over a 10-day period. And the plot on the left side kind of shows where those 10 days are. And so if we were to click on one of these dots on the right side like that, it's going to say that is my sample point. I want to use that day to reflect the IPR. And it gives us a very high IPR. Or if we were to pick one of the lower days, it's going to give us a more conservative IPR. So this is kind of exposing the risk of picking a high or a low day of production. It can change what your IPR shape looks like. What do these different colors mean? Well, a lighter circle means an earlier day, and a darker circle means a more recent day. So on the left side, you can even grab this black line, you could change it, and it's going to associate it with which data point it's picking there, okay? Now, if you want to get really fancy, the 3 blue circles above the plot, you can also turn on show IPR curves, and this will show you the potential range of IPR curves depending on which day you pick to reflect the IPR. Okay, so that we kind of developed this not to scare you, but to show you that it can be important to pick an average or a typical day to reflect the well's productivity. Okay, we're going to do 2 steps. We're going to go back up to the blue dots, and we're going to turn them. We're going to uncheck both of those boxes. Uncheck them. Okay. So what I want to do now is I want to create an average IPR. I want to use the 10 days. I want to create an average IPR, not just using one single day. So kind of up near where that little calendar icon is, there's a button that says average IPR. It might be a little bit over here, but in my case, it's right here. So if you check on AV IPR, it's going to pick a 10-day period, and it's going to, exactly like you can imagine, is creating an average of those 10 days. Okay. Now, if you don't like the start and the end date that it picked here, you can click on the calendar icon. Let's do that. Click on the calendar icon. And you can see that now there's 2 black lines. And I'm gonna zoom in. The way I zoom in is I draw a box, kind of like that. And now, if you wanted to, you could change where the average is based on from the start and the end period, like that. And if you're happy with that, you can click Save in the bottom right. So this might be a more typical IPR, and this is just, again, a way to create the IPR a little more reliably, okay? All right, now it's very likely that everyone picked a totally different range to create the average over. And so to make sure we're actually all on the exact same page, looking at the same thing, I want us to turn off average IPR, turn it off. And I want us to make sure that we're on the most recent day of production, which is 771. And if you're not on day 771, you can click this little arrow here. So this will go like back, this will go forward. So I want you to shift this little blue arrow all the way until you're on day 771, just like me. Okay. Now, if for some reason your orange circle and the black circle are not matching up perfectly, just click this little run button in the top right, and that should kind of sync them up, okay? Great. Let's create a couple tubing performance curves, or VLPs, to try to avoid liquid loading. So way up in the top right here, it says modify cases, modify cases. We're going to click on that. And these rows are where we can do sensitivities on flowing pressure, on tubing size, on flow path, on gas lift rate, on ESPs, on choke sizes, on all kinds of things. Now, what we want to do in this case, before we consider installing tubing, what if we just lower the wellhead pressure to 500 psi? So I'm typing 500 psi under case 2, and I'm going to copy and paste the water gas ratio. So I click on this number, Control C, and Control V. And I might give it a case name. I'll call it lower casing head pressure. And if you've done that, you can click Save in the bottom right. Okay, we should all have a second VLP curve. And so this is if we keep flowing up the casing, but we just lower the wellhead pressure. So if we lower the wellhead pressure to 500 pounds, that's going to give us a bottom hole flowing pressure of 637 pounds, and it's going to increase our gas rate, more drawdown. So that's benefit number one. The other benefit is look at the liquid loading. So if we keep the casing pressure high, we have to stay above 6.5 million if we want to keep the well above the critical lift rate. But if we lower the casing pressure, we can go all the way down to 4.5 million before we have to worry about liquid loading. And the reason for that is when we lower the wellhead pressure, the gas is expanded more. It's under less pressure, so it's expanded. And the bottom hole pressure being lower, the gas is also more expanded downhole as well. So when the gas is expanded more under less pressure, it moves faster. And that faster gas, that velocity, that's our friend when it comes to liquid loading. So that's why we can produce to a lower rate before we worry about liquid loading at a lower wellhead pressure. All right, let's try installing some tubing in the well. So go back up to modify cases in the top right. Now, in here, we're going to go up to the very top right where it says add/edit well configuration up in the top right. We're going to click on that. Okay, so the way the well is set up now is on the left side. It says current, but on the right, we're going to type in a name, and I'm going to type in 2 7/8. Now, down under where it says tubing data, we're going to click this blue plus symbol on the right one time. So this is where we can describe the tubing depth, the tubing size. So I'm going to put my tubing at 6,500 feet. 6,500 feet. And for the tubing diameter, I'm going to use the it looks like 3 pancakes. to me. So on the far right side, we're going to click on this blue icon. And this is where we have our tubing table. So I'm going to go down. I'm going to find 2 7/8, 6.4 pound. This row right here. So click on that row, 2 7/8, 6.4 pound. Awesome. Okay, one last step, the flow path. We're going to change it from casing to tubing. You know, if anyone ever flows up the annulus or the tubing and the annulus at the same time, those are options, but we're going to pick tubing as the flow path, okay? And then we're going to click save in the bottom right. Okay, so we're going to use row 3, but notice there's a column that's called configuration. So down in row 3, I want to click on current configuration, and I'm going to change it to 2 7/8. This is the wellbore description that we just saved for tubing flow. And what I want to do is I want to take this casing pressure 967. I'm going to copy it. I'm actually going to paste it into this column called tubing pressure, right? Because now we're flowing up the tubing, we need to use that line pressure at the surface as our tubing pressure. The casing pressure is not even going to matter. It's not going to be used. So all we really need is this tubing pressure input here. I'm going to copy the water gas ratio into row 3. And I'm going to give it a name. I'm going to call it 2 7/8, like that. So if yours looks like that, again, it's really important that we pick the configuration that we made. Then you can click save in the bottom right. Okay, we should see a yellow VLP line here. So this is with 2 7/8 inch tubing. And the first thing we notice is we slightly reduce the rate of the well because with tubing, there's more friction. So we have a slightly higher bottom hole flowing pressure with tubing compared to casing. But the benefit of the tubing is liquid loading, right? See where the yellow line becomes dashed? We can flow this well all the way down to 1.7 million cubic feet a day before we have to worry about liquid loading. So that's the benefit of putting tubing in the well. Okay, I want to do this one more time, but I want to do an even smaller tubing now, 2 3/8. So if you think you're comfortable with the steps, go ahead and do it on your own. I'm going to do it as well, so you can follow along if you want. So modify cases, top right, add/edit well configuration up here. Give it a name 2 3/8, like that. Under tubing data, we'll click the blue plus symbol. My depth is 6,500 feet for the tubing. I'll click on the 3 blue pancakes over here. I'm going to go pick 2 3/8, 4.6 pound. That's what I'm picking. 2 3/8, 4.6 pound. Flow path, tubing, and then save. Okay, so in the configuration, down in row 4, I'm going to pick 2 3/8. That's what we just described. And then I'm going to copy these numbers from row 3 and put them into row 4. Control C, Control V, and I'll give it a name, 2 3/8. So if you've done that, you can click save. Okay, and we get a 4th VLP, it's the blue one. So with smaller tubing, there's more friction. So we have a higher bottom hole pressure. We back the well out a little bit more. But the benefit is we can avoid liquid loading even further, down to 1.1 million a day. That's where the dashed line begins with the smaller tubing. So when it comes to sizing your tubing, this is a quick way to see, what the rate will be, what the liquid loading rate will be. Now in this case, I'm flowing up the tubing, but maybe annular flow is an option for you. So those are other sensitivities you could do. You could flow up the annulus and see if there's a good trade-off there compared to tubing flow. Okay. I want to give everyone a quick break here. When we come back, we're going to wrap up with this gas well. We're going to do chokes and create a report card of lots of wells to see which ones are liquid loaded. So I want to give everyone a 10-minute break. So let's get back here at 10:35 Central Time. So we'll do a 10-minute break, and I'll see you guys back in 10 minutes, okay? And you can put any questions you want in the chat window in the meantime as well. Thanks. Yeah, Pablo had a question. What if you increase the drawdown to fix liquid loading and mobilize more water? Absolutely. In fact, that's the all right. I think we're ready to get back in here. I'll give people 30 more seconds and we can get going here. Okay, so we're going to talk about chokes. So we're going to take this gas well and we're going to predict what the rate would be at different wellhead choke sizes. Okay, so to do that, we're going to go back up to the top right where it says modify cases. Once we're in there, we're going to go to the top right where it says add/edit well configuration up here. Okay, we're going to type a name in. I'm going to type in wellhead choke like that. And then under tubing data, we'll hit the plus symbol. We're going to use 6,500 feet again. And then for our tubing size, we'll pick the little 3 stacks over here in blue. Now I'm going to pick 2 7/8, and it will be the 6.4 pound row. So 2 7/8, 6.4 pound. Now our flow path will still be tubing. Okay, so we've done all this before, but now we're going to add a wellhead choke. So over on the right here, it says choke. And from there, we're going to pick wellhead choke. Now you get this little pop-up. We don't have to actually change anything here. It's just a preview. We know that the depth is going to be at the surface. We're actually going to type in different choke sizes. So we're going to be able to do different sensitivities on different choke sizes in a more tabular way. So with this pop-up, you don't have to change anything. You can just hit save or close. So yours should look like this. You've called it wellhead choke. You've given it the tubing depth, tubing size, flow path is tubing, and we picked wellhead choke. Okay, and again, if this pop-up happened, you can just close it. That's fine. So once you've done that, you can click Save in the bottom right. Okay, now what we want to do on these extra rows, we want to go to the configuration column. And in there, we want to pick wellhead choke. And I'm actually going to pick it 3 times, like this. We're going to try 3 different wellhead choke sizes. So there's a new column that's called choke size, and it's in 64ths of an inch. So I'm going to start by putting in 40, 32, and 24. So these are the 3 choke sizes I want to try. 40, 32, and 24. Now there's a new column that we haven't seen before. It's called line pressure. And so the way we describe it is, imagine that there's a choke on the tip of my finger. The line pressure is the pressure downstream of the choke. We call that line pressure. The pressure upstream of the choke, we call it the wellhead pressure, or tubing pressure in this case. So we're actually going to use the line pressure column this time. And so what I'm going to do is I'm going to copy the 967 psi pressure that we had as tubing pressure, and I'm going to paste it here as line pressure like that. Because that's basically the pressure downstream of the choke. I'm also going to copy this water gas ratio like that. And there's only one more thing to do, is I want to give case names that are kind of descriptive. So I'm going to copy these choke sizes. You can copy all 3 columns, all 3 cells, and I'm going to paste them as the case name, so I know kind of what I'm referring to when I'm seeing my VLPs. I'll wait a second for people to get caught up. Just make sure your configuration is set to wellhead choke for all 3 rows on the bottom. We've copied and pasted the wellhead pressure into the line pressure column. I've got my water gas ratios copied into. And again, I copied and pasted the choke size as the case name, just to be descriptive. Okay, so if we've done that, we can click Save. Now I have a lot of lines on this screen. It's probably too much for me. So kind of to clean things up, we can go up to this table at the top. I might uncheck some of these just to clean things up. I'm going to uncheck 2 3/8. Okay, so basically I unchecked 2 of them, lower casing head pressure, and I unchecked 2 3/8. So what we're seeing is the black VLP is if we flow up casing. The yellow line is if we flow up tubing with no choke. The pink line is if we put a 40 64th choke, so a big choke. The green line is a smaller choke, and the blue line is the smallest choke at 24 64ths. Okay, so these are all wellhead chokes. If you happen to do a downhole choke, you do the exact same process, but instead of picking the wellhead choke, you can pick a bottomhole choke and you specify the choke size and the choke depth. Okay, with wellhead chokes, it's a bit easier because we know it's at the surface. We don't have to specify a depth. So yeah, for you, this just means that you can quickly kind of sensitize on choke size and see if it's going to reach the target rate that you're aiming for, so you can size the choke properly. Okay. One last thing for gas wells, and then we're going to dive into the oil well, which is a little bit more interesting because we can talk about artificial lift and stuff like that. So what I want everyone to do is go up to the top left where it says projects. Projects. Okay. Now you'll see a project that's called Mass Well Liquid Loading, and there's 27 gas wells in here. And what I want to do is create a report card about which wells are liquid loaded, right? I don't want to manually have to look at them. I just want a report card. So we're going to click on this project called Mass Well Liquid Loading under projects. There's all 27 wells there. And I've already run the bottomhole pressures on these wells. And the way you can actually batch do that is you pick all the wells that are turned on. You don't have to do this because I've already done it, but under run will let you batch run the bottomhole pressures. It'll let you batch run flow material balance. There's all kinds of batch run things you can do here. And I've batch run the bottomhole pressures already. So that's done. So there's a button here called results. And depending on how much you're zoomed in, like if you're zoomed in like a lot, then you might see results over here. Or if your resolution is a bit different, you might see results in the top right. But we want to find that blue results button. So we can click on that. And along the top, there's a couple little buttons here. Right now it's on custom, but we want to click on the next one called liquid loading right there. Now, I'm not sure if you guys are seeing the same columns as me. You might have a lot more columns turned on. Maybe somebody can comment in the chat window if yours looks the same as me or if you have lots of columns turned on. I just want to check. Okay, you see the same as me, Mohammed? Okay, Erica sees lots of columns. Okay, let's show you how to clean those up. So what I want us to do is there's on top of the columns, you can basically, right now, this is probably what yours looks like. It's just like a mess, right? So I want you guys to uncheck all the columns. So you're starting with like a blank slate like that. We're going to turn on well name. We're going to turn on current gas rate. We're going to turn on Turner critical rate. And then there's something called comparison. And we're going to turn on Turner under comparison. And there's only one more. It says percentage, and we're going to turn on Turner percent. So we should have 5 columns in total. Now, before I explain these results, I want us to kind of sort these. And the way we're going to sort them is on the top right, it says table sort by up here. What I want to pick in there is I want to find the percent Turner. So you scroll way down and find Turner percent from that table sort by in the top right. Turner percent. All right. So this is reporting the current gas rate, what the critical rate is, the minimum rate to lift liquids, and then it's reporting the difference. So wells that are in red means we're liquid loaded, we're below the Turner rate. Wells that are in green mean we're above the Turner rate. Okay, now this is not only taking the most recent day, but it happens to be taking the 10-day average. So this is something that you could do maybe once a month. You come in here and your daily rates and pressures are typically automated and coming into Whitson. And if they're not, let us know. And so this is something you can kind of look at every month to create a report card about which wells are liquid loaded. And then you can really focus on just those wells to do different tubing performance curves, tubing sizes, things to mitigate liquid loading. Okay, so again, that's under projects. You pick your wells, you go to report, and that's how you can see these liquid loading results.
Can you show it quickly again, Graham, how to go to project to the wells and then
yeah, absolutely. So up in the top, up in the top left, projects up here. And we're going to go to this project we hadn't used before. It's called Mass Well Liquid Loading, where we have 27 wells. And we're going to click on that project called Mass Well Liquid Loading. So we should see a list of wells here, and we're going to look for a blue button that says results. Results. If it's not up in the top right, it just means that you're kind of zoomed in, and maybe results is over here instead, depending on your zoom. So once we click on results, by default, it goes to something called custom, but we want to click beside that to liquid loading. And then if you have this buffet of columns, it's too much, you can uncheck all the columns like I did there and only turn on well name, current gas rate, Turner critical rate, and then under comparison, Turner, and under percent, Turner as well. One thing I've seen people use this for is if their results are looking weird or kind of blank, that can be a way to flag that there might be something missing in the wellbore, right? Or there might be, again, this is just a bit of a QC thing. If there's something very weird or just blank, it means there's probably something missing in the wellbore description to calculate the bottom hole pressures. Okay. Let's look at an oil well and talk about gas lift and different kinds of artificial lift here, okay? So back up in the top left under projects. In projects, we're going to go to the project called main. So under projects, click on the row called main. And instead of the gas well, we're going to use the oil well. Oil well. Once you're in oil well, the first thing we want to do is make our own scenario so that we're not stepping on each other's toes and analyzing the exact same well and kind of overriding each other's work. So in the very top where it says scenarios, we're going to say add new scenario. And you guys are ahead of me. So under scenarios, add new scenario. I'm going to call it my name. And then you can click save in the bottom right. So your scenario is like your sandbox. You can do whatever you want and not affect anyone else's work. Okay, so you should see your name under scenarios. And then we're going to go to the left where it says PVT. We'll click on PVT. Man, someone was already in here. That's okay. We're going to go to this little square box up here under PVT. Okay, and this is typically what you're going to see if you have an oil well or a gas condensate well, is we're showing you the initial GOR or maybe CGR of your well. Okay, in this case, it's about 275 scuffs per barrel, so pretty low GOR. We've got our reservoir temperature in here. We've got our initial reservoir pressure. And these are really the only three things you need to make this equation of state model work. Initial GOR, initial pressure, and reservoir temperature. All right, so we're going to click to the bottom right and say save. And we should get this beautiful phase envelope. So this is our initial reservoir pressure, and it's actually predicting a bubble point pressure of about 1,500 pounds. That's what the equation of state's doing for us. So you would find is if you had like a well with a much higher GOR, then this bubble point is probably going to be predicted to be higher. And so a lot of the people on the call, you guys have kind of joined our consortium where we have calibrated equation of state models for the Eagle Ford, for the Permian, for the Montney, all these Duvernay. And so the default in the software that we're using right now is called the Peng-Robinson equation of state. That's what we're all using right now. But you'll find when you get back to your office, if you're working, you may find that the a phase envelope might look a little bit different because a lot of you guys have these optional kind of calibrated equation of state models that are unique to each basin through North America. But for now, we're using kind of the generic one called Peng-Robinson, okay? So we've got our phase envelope. Next step. On the left side under PVT, it says production data. We'll go there. So this oil well's been producing for less than a year. And it looks like there was a big shut-in here in the middle for some reason, okay? So up in the legend, I just want to look at the oil for a second. And so I could either like uncheck everything, but again, remember the shortcut in the legend. If we double click on the word oil, and you have to double click on it really fast in the legend, now we can see the oil rate. So it was initially 1,300 barrels a day. Now we're down to around 400 barrels a day oil. Here's our gas rate, our water rates. We have tubing pressures. We also have casing pressures, okay? Now this well happens to be on gas lift as well. So I turned gas lift on in the legend. Now it's kind of hidden in there. So if I want to only see gas lift, I'm going to double click on the word gas lift in the legend. Double click like that. Again, if it's not working, we got to work on our double click skills to go even faster with the double click. So for the first month and a half, the well was not on gas lift. And then gas lift came on pretty low, around 50,000 scuffs a day. And then later 350,000 scuffs a day gas lift. And now we're around 200,000 scuffs a day for gas lift. Again, there was a big shut-in in the middle. That's why we're not seeing any gas lift. So that's kind of the history of this well. Let's calculate the bottom hole pressures. So on the left side, we'll go to bottom hole pressure. I think someone was in here already working on the main scenario. That's okay. Okay, so we've got the pump jack. And up in the corner of the pump jack, we're going to click on the little square up here. Okay, and the first thing we see is this deviation survey. We can click on the little blue icon above the table. Looks like a little blue curve. And the first thing I'm noticing is this well appears to be toe up. Sorry if you heard my dog in the background there. So this well looks to be toe up, just a little FYI. Okay, let's close this pop-up. And we're going to go to the top right where it says well data up here. Well data. So the first thing we're noticing is we've got casing data. We've got 2 3/8" tubing. And initially the artificial lift method is none, right? Because the well was naturally flowing for the first month and a half. Now up in the top left, we have configuration 1, and then we have configuration 2. So let's click on configuration 2 on the left. And we notice that there's a date. So these configurations are really whenever there was a change in the wellbore, like a tubing change, a flow path change, an artificial lift change. Even if you change gas lift valves through the well's history, you can add that configuration to reflect what's new in the wellbore. So we've clicked on configuration 2, and if we go down, we see artificial lift method is set as gas lift. Awesome. I'm going to talk about some of the different artificial lift methods before we get into gas lift. So if we open the artificial lift method, we see that there's a few options. Okay, jet pump. We might have some people who are using jet pump. If we pick jet pump, this brings up this pop-up where we can put the depth of the pump. We specify what our power fluid is, the nozzle diameter, things like this. So this will let us calculate the bottom hole pressure through a jet pump. Okay, and this can also be used on the Nodal Analysis to do different jet pump configurations. Okay, let's close that screen. We have ESP. Let's look at ESP. So the first thing that pops up is this big menu, and this is for people who don't have a pump intake pressure on their ESP. So what this lets us do is it lets us specify, well, basically there's a list of 600 different ESP models in here that you can pick from. And then you can specify the depth of the pump, the number of stages, things like that. And this will actually take the tubing pressure, calculate the pressure down to the pump outlet, calculate through the ESP, and calculate all the way down to the perforations. So this is for when you're lacking a pump intake pressure, even temporarily on the pump, okay? It lets you calculate all the way down to the bottomhole pressure through the pump. Let's close this pop-up. But maybe more typically is that you do have a pump intake pressure on an ESP. In that case, you would type in the depth of the pump intake down here. We call it gauge depth, but it's really the pump intake depth. And you could turn on this little box. And what this would do is it would take your pump intake pressure and it would convert it down to the pressure at the perforations. Right? Typically our ESPs are set above the perforations, but when we're doing this analysis, we want to get the pressure way down at the perforations. So by specifying the pump depth and checking this box on, it'll use the pump intake pressure and add the delta P below all the way down to the perforations. Okay. I'm going to uncheck that box, make sure it's unchecked down here. Okay, rod pump. So with rod pump, you'll notice that when you pick rod pump, it says compute through quiet side, which is typically the annulus. With rod pump, we have this pump, this rod in the way that really makes the tubing pressures not very useful to calculate the bottomhole pressures. So with rod pump, we want to use fluid levels. So in the production history of your well, you can input all the fluid levels that you have through time. So this will use the quiet side or the casing pressure, do a static gas gradient down to the fluid level that's been specified through the history, and then do another gradient down to the end of tubing, and then a multi-phase calculation down to the perforations. So if you have rod pump, you want to get the daily bottomhole flowing pressures, we need fluid levels through time, and you'll use the quiet side pressure to get the bottomhole pressure. That's rod pump. Okay, the last one is plunger lift. And this even works when you're doing plunger with gas lift. So if you click on plunger lift, we get this little square box beside plunger lift. We can click on that little square box. So this is where we can input the plunger depth, how many minutes the well is open and flowing during like a plunger cycle, how long it's shut in, and how long it takes for the plunger to travel. So what this does, because we know plunger lift is kind of intermittent through the day, what we do is we take the daily gas rate that the well's produced, you know, that's reported, but we want to convert that into the instantaneous rate while the well is actually flowing. And the reason we do that is when we use the tubing pressure, we want to calculate the bottomhole pressure, right? But the rate that we want to use is not the average rate of the day. We want to use the instantaneous rate during the production period of the plunger lift. So again, by putting these inputs in here, it will figure out what the instantaneous rate is during the production period during the day, and can use the tubing pressure to get the bottomhole pressure for the instantaneous rate. So the right friction and everything like that during the instantaneous rate. Just an FYI, okay? So let's close that pop-up, and we're going to change artificial lift method to gas lift. Gas lift. So what are some of the ways we can do gas lift? Well, right now it says gas lift configuration valves, but if we open that up, we see 4 options. Pour buoy. Pour buoy is just as when we're injecting all the way down to the end of tubing and coming up. Or maybe if you have reverse gas lift where you're injecting down the tubing and everything's producing up the annulus, we can do that too. So pour buoy is just where we don't have valves, we're just injecting all the way down to the end of tubing. So let's talk about automatic for a second. This is where we have gas lift valves, but we don't know the valve depth And we don't want to assume poor boy. So what does automatic do? So it's going to take the daily tubing pressure and the daily casing pressure. And it's going to do two calculations at the same time. It's going to calculate the pressure down the tubing, and it's going to calculate the pressure down the annulus. It's going to do those separately. It's going to figure out at what depth are those pressures the same. And it's at that depth where the pressures are the same that it will assume that there's an open valve. So again, automatic is for people who don't really have they have valves, but you don't have the valve depths, and you don't want to assume poor boy. So automatic works well as a way to estimate valve depth by calculating down both the flowing side and the injection side for gas lift at the same time to figure out where those pressures are equal. So that's what automatic is. Valves is what we're going to use here. So when we pick valves, we get this little square box that we can pick on right here. We'll click on that square box. And this is where we can put our valve depth. Here I have 4 valves. We also can put the PSO, which is pressure surface open, and pressure surface closed. So these are the criteria for pressure required to open or close these valves. So this is all an input, right? You can get this from your valve manufacturer. So what the software is going to do is it's going to take the casing pressure every day. It's going to refer to this table of PSO, PSC pressures and determine which valve is open based on the casing pressure. Okay. Now, if you have these details in the database, like in WellView, all of this can be automated and brought into Whitson, so you don't have to like manually type it in. Okay. If you've got these valve details in some separate spreadsheet that's not really, able to automate it, we also have this Whitson kind of template, like an Excel file, that you can kind of bulk copy and paste all these details in, and then you can do like a mass import into Whitson. So you can either automate this in through like an API connection, or we can help you bulk import these through a spreadsheet. Just reach out to me or support@whitson.com if you want help with that. All right, let's close this screen, or close this pop-up, and we'll close this other pop-up. So we're going to get back to this page. So we're ready to calculate a bottom hole.
Hey, Graham.
Yeah, go ahead.
Real quick, can you show how to get back into the well data and the deviation survey?
You bet. So we've got the pump jack symbol here. And then there's this little square box up in the top right. So if we click on that, we see the deviation survey right here. And then if you click on well data up in the top right up here, this is where like our tubing and our casing and artificial lift description is.
Perfect. Thank you.
Yeah, you bet. Yep. So I'm gonna close that screen. So let's click this big blue button, calculate bottom hole pressure in the top left. So we should see these calculated bottom hole pressures below, and we see, the blue one, Beggs and Brill, has the highest BHP, gray has the lowest BHP, and that's kind of in line with that BHP study that I showed you, the paper. But we all know that our new favorite correlation is Waldesbach-Gahar. So I want us to make sure that in the this drop down at the very top, make sure we're all selected on Waldesbach-Gahar. Okay, that's what we're going to pick and use for this well. All right. So under the pump jack, we're going to click on this little thing that says liquid loading plot right here. Now, I mean, for a very low GOR well, do I care about liquid loading? Maybe. I mean, I know for gas condensate, people definitely care about liquid loading, but it's still handy to look at this. So again, our blue line is the minimum gas rate needed, in this case, at the end of tubing, to get above our critical lift rate. Now, this well has reservoir gas, but it also has gas lift gas. So the dashed red line at the bottom, this is how much reservoir gas is being produced. Not enough to get above the critical lift rate, right? If we look in the legend, it says gas lift rate. We can turn that on. So the middle red line is the gas lift rate. So we have two gas sources, reservoir gas and gas lift. And when you combine them together, you get the top red line. So our total gas coming up the wellbore from the reservoir and from gas lift is still not enough to get above the critical lift rate. So effectively this well's liquid loaded. That doesn't mean the well's going to die, right? When liquid loading, every well's going to respond different to liquid loading. The well's not dead. It's still producing, but we're below the critical lift rate. So for people, if your objective for gas lift is to remain above the critical lift rate, then you want to see this dark red line above the blue line. Okay. Under the pump jack, we're going to click on this tab that says gas lift plot right here. There's a lot of stuff on this plot, but the only thing I care about are the blue dots. So in the legend, it says gas lift valve depth. And I'm going to double click on that so I can only see the blue dots. So what this is showing is the estimated open valve depth through the well's history. So initially, we were injecting at the 3,000 foot valve. As time went on, we get down to a lower valve, 5,000 feet. There was a big shut-in here in the middle, so that's why everything's missing. And now we're all the way down to the bottom valve at 7,000 feet. All right, so if you either use automatic gas lift or you specify the valve depths, you're going to be able to quickly estimate, am I on the bottom valve? Which valve am I on? And that can just be a really quick-handed diagnostic, okay? So good news, we're on the bottom valve now. And this is all dictated by the casing pressure and then those PSO, PSC pressures that have been input for the valves. If you're kind of trying to remember, what were those valve design? What were the valve details? Above the plot, there's a little 4-window pane that looks like this right here, above the plot. And if you click on that, it's going to give you a quick reminder of those valve details. Okay. Okay, there's one last thing we're going to look at before we do like the IPR VLP stuff for this well. And under the pump jack, I want to go back to where it says BHP plot. Okay, under the pump jack, BHP plot. So somebody has put an initial reservoir pressure of 5,650 pounds. Who knows if that's right or not, right? So what I want to show you is a quick way to estimate initial reservoir pressure just using some very early time flowback data. So above the plot, we've got this little green check mark, and you'll see beside that there's something that says estimate initial reservoir pressure right here. If we all click on that, we get this plot that shows bottom hole pressure versus oil rate. And it's showing us 10 green dots. So these are the very first 10 days of production where we have hydrocarbons, and it's showing what the rate and the calculated bottom hole flowing pressure is for those first 10 days. And the idea here is if you click on this blue autofit button in the top left, autofit, it's going to try to put a line through those points. And the idea is the place that this black line points back to and intersects on the y-axis, that can be an estimate of your initial reservoir pressure. All right, so if someone's doing a defit or you have a downhole gauge, those are good ways to get initial reservoir pressure, but this is just another way to very quickly check without a lot of work. If somebody has a gas well, you would change this IPR type on the bottom, you change it from oil to gas, So this is just a quick FYI. This doesn't always work. It really depends on some of the data quality. Sometimes your data might be all over the place, but it's worth a try if you have some doubts about the initial reservoir pressure. Okay, now I'm not going to, if you click save, don't worry about it, but save is going to actually go ahead and use and apply this new initial reservoir pressure number. It's not a problem if you click save. I'm just going to click X to get out of here, and I'll keep whatever somebody had put in here before. So it's not going to matter too much, okay? All right, IPR curves for oil. So very similar to the gas well, it's just a slightly different equation. We're trying to figure out what the oil rate will be. J is like the well's productivity. This is our current reservoir pressure, not our initial pressure. We want to know the current reservoir pressure. This is the bottomhole flowing pressure. So what's in the brackets is basically the drawdown of the well. So how do you use a well that's currently producing to get the oil IPR? Just like we did with the gas rate. So we need to say, what is the current average reservoir pressure? 2,000 pounds. What is the well's current rate? 100 barrels a day at a bottomhole flowing pressure of 1,200 pounds. Right? We plug in the oil rate, we plug in the bottomhole flowing pressure, and that means we can solve for J. Effectively, we get a line through the reservoir pressure, the current operating point, and we get this IPR curve, right? Now, this looks like a straight line, but once we go below the bubble point, we can actually say, what is the bubble point pressure? That's already figured out for us. Remember, we did the equation of state. We made the phase envelope, so it figures out the bubble point for us automatically. And that actually adds this curvature that we typically see on an oil well below the bubble point. So just a little bit of background. This is probably a review for lots of you guys, okay? But let's figure out this question. What is the current average reservoir pressure for this well? So we're going to go to our flowing material balance on the left side here, flowing material balance. We're going to click the blue run button. Okay. Now I want everybody to go ahead and try to match the black slope. Again, you can change the slope by grabbing the end of the line. Try to match it however you see fit. I'm going to do something like this. We're trying to find the most shallow slope that we can see. So if I were to match like the early time data, that would be too conservative. It would say my tank is too small. So we're trying to find the most shallow slope we can get. And by the way, like in the chat window, I pasted a link to a flow material balance course that goes through this in much, much more detail. For now, we're just going to try to find a slope that we think looks reasonable here. Now, by the way, a lot of your reservoir engineers have probably already done the flow material balance on your wells. So if you go into your wells, you probably already see this done. And if you're not sure about your interpretation, either ask your reservoir engineer or ask Whitson. We can look at it with you, okay? All right, so from my interpretation, I'm getting about 3 million barrels of oil in place on the left side. So that is how big the tank is. We're estimating that's how big this oil tank is, this reservoir. That's how much we're draining from. That's the estimate based on this slope. You guys might be a little bit different. It's okay. So once we've made that interpretation, we're going to click run, and that's going to update the pressure plot in the top right. Let's expand this pressure plot with this little 4-arrow box right here, expand. Okay, now I want anybody who sees something concerning about this to speak up or type in the chat window. Do you see anything that's a bit concerning about this? Okay. So the thing that's concerning about this is we have our gray dots, which are calculated bottom hole flowing pressure. And the black line is the average reservoir pressure. And the thing that's concerning to me is that over here, right? The well was shut in, then we get some flush production. It shows that the flowing pressure is higher than the average reservoir pressure. And that's impossible. Our average reservoir pressure, our black line, should always be above the flowing bottom hole pressure. So this is very common to see this when you're looking at your wells, and it's a clue that we've made our reservoir interpretation, the size of the reservoir, we've made it a little bit too small. If we increase our interpreted size of the reservoir, it's going to cause the average reservoir pressure to go up above the flowing pressure. So again, this is a big clue, and it's very common for people doing flow material balance to see something like this. So let's use that clue. So I'm going to kind of shrink this pressure plot down so I can see my FMB again. So how do you make the reservoir bigger to get this black line up? Well, you basically grab the slope and you try to make it a little more shallow. So if you were to make it more shallow, again, we're all going to have our own interpretation here. So I'm going to just try something like this as an experiment. It's going to be kind of a bit of an iterative process. So before, my tank was about 3 million barrels, and I made my slope go from this down to this, and that increased it to about 3.8 million barrels in size. So the shallower the slope, the bigger the size of the tank that we're interpreting. So try to make your slope a bit more shallow, so it's around 3.8 million barrels in place. And if you've done that, you can click Run. That's going to update the pressure plot. If I go and look at my pressure plot, I'm going to expand it again in the top right. We notice that the black line, the average reservoir pressure, it moved up, right? We're saying that if we have a bigger reservoir, we have more reservoir pressure remaining. So now I've only got really 2 points where the flowing pressure appears higher than the black line. I'm not too worried about that. You know, maybe there was, I'm not gonna, like, if you wanted to, you can move the black line a little higher if you wanted, but I'm quite happy with this. And I'm saying that my current average reservoir pressure is around 3,000 pounds. If anyone's seen something way different than 3,000 pounds at the end of the black line, go ahead and type it in the chat window, and one of our guys online will help you out. So again, 3,000 pounds, current average reservoir pressure. I want that for the IPR curve. All right, let's go down to the bottom left where it says Nodal Analysis. I think someone was in here already. Okay, so we want to uncheck average IPR. By the way, you're not going to see this normally. It's just because someone was playing in here. So uncheck average IPR. And we're going to click on this calendar icon right here. Okay. And we're going to take this vertical black line that we see right here. We're going to drag it all the way to the end and let go. And that's going to ensure that we're all in the same day to create the IPR. If you've done that, you're going to click Save in the bottom right. Let's see, what else do I have to do here? Oh, you know what? Someone's changed this to a gas IPR. So up in the top left, we're going to see where it says IPR type CNN gas. We're going to change that to Vogel. I'm going to do a little clicking around to make this appear like it should when we get in here. Okay, so the first thing I want to do is on this plot in the bottom, we're going to reset the zoom. So just double click in the plot. Like for me, it was looking something weird like this. If you double click on the plot, it should reset the scale like that. I'm going to And if it's still not working, a couple of little tricks you can do is make sure you're on day 250 here. You can toggle over with the little blue arrows to get on day 250. And then if it's still not working, click this little run button for the VLP here. If anyone's screen is not looking like mine, go ahead and ask something in the chat window. I'll try to make sure we're all on the same page here. Yeah, so again, the changes that I made is in the top left, I changed IPR type from it appeared to be gas. We changed it to Vogel or oil. I made sure that my day here by the calendar is set to day 250. I double clicked on the plot to reset the scale so I could see everything. And then I clicked on this little blue run button to make sure everything's up to date. Now, normally if you come in here, it should just appear exactly like this by default. We just had to adjust a few things because it was changed before we got here. I'm gonna check the chat window real quick. All right, so hopefully we're all on the same page here. If you're not, just type in the chat window. So this is a snapshot. This is how well the well is operating today. It's receiving 200,000 cubic feet of gas lift. First question we want to ask is, would the well benefit from more gas lift? So to answer that, we're going to go up to the top right, modify cases. Now we've got a column called gas lift rate. I want us to type in 500. So what if we inject 500,000 cubic feet a day of gas lift in this well? For the pressures and the GOR, I'm just going to copy them. Copy, paste, Control C, Control V. And I might give the case a name like more gas lift. If you've done that, you can click Save in the bottom right. Okay, and I get this purple VLP line. And this is showing me that if I go from my current gas lift rate of 200,000 up to 500,000 cubic feet a day, we're going to lower the bottom hole pressure and we're going to increase our oil rate. So the answer is yes, this well will benefit from more gas lift. So the next question is, okay, I just guessed at 500,000. What is the ideal gas lift rate that we could get the highest oil rate for this well? So instead of making a whole bunch of different VLPs manually, there's a quicker way. And it's called the gas lift curve. So what we're looking at here is if we add more gas lift, so let's pretend we have no gas lift on the well at all, then we can typically have a very high bottom hole flowing pressure, right? There's the gradient or the gravity in the wellbore is very high, and we have a very high bottom hole pressure when we have no gas lift. As we add a little bit of gas lift, we can reduce that gradient and we can improve and lower the bottom hole pressure with a little bit of gas lift. As we add more gas lift, we can further reduce the bottom hole pressure, and at some gas lift rate, we're going to be at the very bottom of this bottom hole pressure. So this would be the best gas lift rate that we would use in order to get the bottom hole pressure all the way down here. Now, if we keep injecting more gas lift after that, we actually worsen the bottom hole pressure. We're adding so much gas lift that we're adding friction because all that gas we inject has to come up the wellbore. And so if we're over injecting gas lift, we can worsen the bottom hole pressure due to friction. So what we do is we take all these bottom hole pressure points here and we apply them to an IPR curve. And what that produces is it estimates what the oil rate will be in green at every bottom hole pressure. right? So when we have a high bottom hole pressure, no gas lift, we typically have a low oil rate. As we lower the bottom hole pressure from more gas lift, we see the oil rate improve. And basically at this bottom of the bottom hole pressure curve, that will be the highest oil rate that we can get from this well. And that's how we can estimate what gas lift rate to achieve this at. Now, luckily, this curve is made for us automatically in Whitson. So up at the top, like right now, we're on this little tab that says IPR VLP. But if we go over 2 tabs, it says gas lift opt, and we can click on that. And we should be seeing a gas lift curve that looks like this. So this is oil rate versus gas lift rate. So the peak of this curve is this circle. So the highest oil rate we could achieve from this well is about 560 barrels a day if we inject 1.1 million cubic feet of gas lift. Where are we operating now? Well, that's the X. Currently, we're only injecting 200,000 cubic feet of gas, and our oil rate's 430 barrels a day. So the difference between where we're operating now and where we could be operating is the difference of 123 barrels a day. So basically, we're leaving 123 barrels a day on the table by under-injecting gas lift. The dashed line is our critical lift rate. So if we're worried about liquid loading and we're saying how much gas lift do I need to avoid liquid loading, that's where the dashed and the solid part of the line join. So we need to inject about 550,000 cubic feet a day of gas lift if we want to get over the critical lift rate. Okay. Now for some of you guys, this might be the first time you've seen a gas lift curve. I know I only learned about it about 2 years ago, but I have to say it's kind of my favorite thing to use for gas lift wells because it just tells you so much in one picture. Okay. So again, X is where we're operating now. The circle is the peak oil rate we could get from gas lift. Now, if you're worried that your wells are over injecting gas lift, then your X, which is where you're operating now, the X would actually be over to the right of the peak. Okay, so over injecting gas lift is basically means your X, your current condition is to the right of the peak. That's over injecting. Now, something you're probably observing is the shape of this curve. As you inject more gas lift, you kind of have diminishing returns on how much more oil you get, right? This curve kind of flattens out. So if you want to say economically, where would be the best place to operate along this curve? This is kind of a new thing. Just down in the bottom left, there's a little box that says economic optimization down here. And if you check that box on, you can enter the oil price, which is about 90 bucks a barrel right now. The gas price, which is, I don't know, is it like 320 or something? And then how much does your lift gas cost in dollars per 1,000 cubic feet? So what this does is it puts a new star, kind of like a diamond, on the curve. So like as oil price goes down, maybe like if it was 40 bucks a barrel, you'll see that it makes sense to inject less gas lift, or if your gas price, or if let's say your lift gas is very high, like $2 an MCF to lift, it's going to tell you that you should inject less gas. So this is just a quick way to find the more economic place along this curve to inject gas, not just the kind of mechanical peak of the curve, okay? Okay. So we know that if we want to get 560 barrels a day, we need to inject 1.1 million. Let's go back to our IPR VLP on the top left up here. IPR VLP. And I want to kind of recreate the max oil condition at 1.1 million of gas lift. So the way we do that is up where it says modify cases up here. We'll click on modify cases, and I'm going to put 1100 in the row, in the third row. That's basically what my gas lift curve told me is how much gas lift is needed to get the maximum oil rate. So I can copy the pressures like that. I'll type in max oil gas lift. And if you've done that, you can click save. Okay, so this yellow VLP is the absolute highest oil rate I can get from gas lift. If I inject more gas lift than 1.1 million, I'm going to be adding friction. I'm going to actually worsen the bottomhole pressure, and I'll reduce my oil rate. So 1.1 million is the mechanical maximum gas lift rate in order to get the highest oil rate. And I learned that from the gas lift curve where the peak was. Okay. Okay. One last thing we want to do. I want to say, what is the pressure loss along the lateral for this wellbore? Okay. The way we're going to do that is up in the top, right? We clicked on IPR VLP. We looked at the gas lift off tab. We're going to click on the one in the middle called gradient right here. So what this is doing is it's taking the well's current condition, right? We're injecting 200,000 scuffs a day. This is kind of a snapshot of how the well's operating today. So the plot on the bottom left is showing our TVD versus our pressure in the wellbore. So back up at the surface, we're at like 150 pounds tubing pressure, and we can see what the calculated pressure is through the wellbore for TVD. I personally like MD a little bit better, so above the plot it says MD. We can click on that. So now we're showing measured depth versus pressure in the wellbore. And so what I'm seeing here is this is the heel of the wellbore, and this is the toe of the wellbore. And I can see what the calculated pressure is everywhere in the wellbore. So at the heel, we're around 1,700 pounds. And at the toe, we're actually lower. We're about 100 pounds less. So there's 100 PSI pressure drop along the lateral, and it's higher at the heel. Does anyone have any guesses why the pressure is higher at the heel and lower at the toe for this well? I'll check the chat window. Toe up. You guys were paying attention. Yeah, if you remember when we looked at the deviation survey for the wellbore, the well was toe up a little bit. And so because this is an oil well, you know, the oil weighs a lot, right? So basically this is the toe, and then the pressure is highest at the heel because of the gravity and the density of that oil, you know, going down the wellbore. It's lower here. So that's why there's higher pressure in the heel. Awesome. You guys were definitely paying attention. All right. Let's go back to where it says IPR VLP for a second on the top left up here. So the highest rate scenario here is our yellow VLP. That's where we inject 1.1 million, right? What I want to do is I want to look at that case, but on the gradient plot, right? Like right now, we're looking at how the well's operating currently. That's what the measure depth versus pressure plot was. But I want to look at the same thing for this case where I'm injecting more gas lift, 1.1 million. So we've got 3 rows, right? Current, more gas lift, and max oil. So in the bottom row, I want to go way over to the right where we see 3 little dots on row 3, 3 little dots. So I'm going to click on those 3 dots and say send to gradient. Send to gradient. So again, I'm going down to row 3 along these cases, go to the far right, 3 little dots, send to gradient. and this name is fine. We can say yes to save to that. So if we go over to our gradient tab at the top, we should have a second gradient here in yellow. So the black one is what the pressure is through the wellbore at a low gas lift rate. And the yellow line is what our pressure is through the wellbore at a higher gas lift rate, 1.1 million. So we can see, indeed, we have a lower pressure in yellow because of the higher gas lift rate. Okay. The next question. Is the pressure loss in the wellbore, is it dominated by friction or is it dominated by gravity? What's the answer? So let's answer that. So we've got these two rows at the top, right? The first row is how the well's operating now. If we go way, way over to the far right, there's a blue 4-window pane over here. I'm going to click on that 4-window pane over here. So what this is doing is it's chopping the wellbore up into segments, and it's reporting what's going on in every segment. Now for me, there's, again, way too many columns here. So I'm going to uncheck everything with this little box at the top. What I want to turn on is I want to kind of expand depth, so like the little triangle, and I'm going to turn on measured depth. I'm going to also expand pressure drops. And the two things I want to turn on, I want to do friction cumulative drop and gravity cumulative drop. So I have 3 columns. So I can see down at 7,000 feet, I'm only losing 50 pounds due to friction. But gravity is causing almost 1,300 pounds of pressure drop. So we know the answer is gravity is dominating the pressure drop in this wellbore. 1,200 or 1,300 pounds, right? This is how the well's operating now. Okay, let's close this screen for a sec. Let's look at row 2. This is where we're injecting more gas lift. I'm going to go back to that little blue window pane on the far right, but for row number 2. And thankfully it saved those column selections. Now, what I'm noticing is for friction, I've added about 200 pounds of frictional pressure drop because of the gas lift. But for gravity, I've reduced the pressure drop from gravity by 400 or 500 pounds because of all that extra gas lift. I basically made the fluid less dense because of gas lift. So this kind of lets you kind of dig into these effects and why is the bottom hole pressure improved with gas lift. It's because we've reduced the delta P from gravity. We've reduced the density of the fluid. Now, if you really want to nerd out, there's lots of other things you could look at. Like one thing that people like to look at is the flow regime, right? We've got these, like for the pressure loss correlations, there's something called the flow map. If you've heard of like mist flow, slug flow, all those things, these are like labels based on the liquid holdup at different points in the wellbore. So if you're curious, what is the flow regime label through the wellbore, you can start to see that as well. Lots of other things you can see in here if you're curious about. Okay, we can close that screen. Okay, so that is really the end of case number 2. The only other things I want to kind of show you guys are how do you, let's say you've got lots of wells on gas lift and you want to start to rank them by which wells will respond more to a gas lift rate change. Some wells may not respond much, and some wells will respond more. And then I want to show you, if you have a limited supply of gas lift that you have to share with many wells, how do you ideally distribute that gas lift for the highest combined oil rate. And then the final thing is kind of where are we going? What's coming next for nodal analysis? So I want to give us another quick break here. So let's get back at the top of the hour. I'm going to give you guys, because we're a little bit ahead of schedule, I want to give you a 15-minute break. So let's get back at, what time is it now? So it's 10:44 here in Calgary. So let's get back here in 15 minutes, and then it's only going to be about 15 more minutes at the end, and then we'll be done. Okay, so I'll see you guys back at the top of the hour. Okay, thanks. All right, I apologize for going a little bit over. There's so much new in the software. I need to work on squeezing it in to this 3-hour period. So the good news is for this last 10 minutes, you guys don't have to click around. You can just watch, okay? So I've got, I don't know, 12 wells here. They're all on gas lift. And I want to answer that question, which wells will respond more to a gas lift change than other wells? So I can kind of rank them. So I've got all the wells selected here. I'm under wells, and what we'll do is go to results. This is the same place that we looked at which wells are liquid loaded. Okay, make sure you guys can see my screen. I think so. Yeah. So results. So instead of liquid loading, which we looked at before, we're going to go to this thing called the gas lift optimizer. Okay, let's make sure. I already did this, but so I'm just gonna. Oh, sorry, I'm in the wrong one. Multi-well gas lift. Here we go. I was in the wrong set of wells here. So there we go. All right. So instead of liquid loading, what we're going to show are some details about the gas lift results for all these wells. So I'll get my well names. I'll see the current oil rate and the current gas lift rate. So this is what the wells are getting now for gas lift, what their current oil rate is. Now, if each well has a gas lift curve, so if we were to go to the peak of the curve, we can see what would the maximum oil rate be if we had a more gas lift compared to the current oil rate, and how much extra gas lift would that require. So we can see the gas lift needed to reach the maximum oil rate, and I think we can show the difference between those two. Here we go, a gas lift rate change. So if we, for example, this particular well is at 438 barrels a day now at only 200,000 scuffs a day. If we were to increase the gas lift rate to 1.1, that oil rate would jump up to 640 barrels a day. So we can start to rank these wells by the oil uplift here. Okay, so this oil rate uplift is showing the incremental oil rate we could get by getting to the peak of each gas lift curve. So, you know, like this well on the bottom, it can only respond by 2 barrels a day. And you can even click on this shortcut over here on the left. So that's going to take us to that well's gas lift curve. And we see that going from here, where we're operating now, to the peak of the curve, it's only 2 barrels a day incremental rate. But if we were to go to like a different well where the uplift is 200 barrels a day, click on that shortcut, and we can see that there's a rate response available. Like this well would respond more to gas lift. So again, this is just kind of a way to rank wells by this uplift from a gas lift rate change. The only simplification or limitation with this is this approach assumes that we have infinite gas lift supply to achieve this. So instead, if we have a limited gas lift supply, we're going to go to something called multi-well gas lift opt. Okay, so this is something I'd recommend using after you get comfortable doing like single well gas lift optimization. But what this is going to do is let us pick wells that are sharing some gas lift. Let's see. There we go. So I've got like whatever 10 or 11 wells here, and their combined gas lift that they're all receiving is about 3.5 million cubic feet a day. That's the combined gas lift all of these wells are getting now. So what I want to do is go continue. When I click this, it's going to figure out if there's a way to redistribute that total gas lift among the wells to get a better combined oil rate. So what I'm seeing is this is how much oil rate each well is currently producing and the current gas lift rate that each well is getting today. Now, this column called optimized, this is where it's figuring out how to best distribute the gas lift. So notice that the totals are the same, where our total supply is 3.3 million in both cases, but the difference is this optimized column is a better way to distribute that gas lift among the wells. And if we do that, the oil rate will go from the current 1,400 barrels a day combined up to 1,600 barrels a day combined. Okay, so that is the purpose of this. It's to take a limited supply of gas lift and say, is there a better way to distribute it? And this column is the recommended amount of gas lift and how to distribute that limited supply. And it can estimate what will the benefit of the reservoir rate be if we do that. Pretty awesome, right? This also works for gas wells. If you're using gas lift on gas wells, you can do the exact same thing here. So some other ways people are using this is to say, okay, right now I have a total supply of 3.3 million, but what if I increased that to 5 million? How would I best distribute that? So we do the same thing. And now we see that if our total supply is 5 million, this is how we would distribute it. And the oil rate would go up another 120 barrels a day or so. Okay, so you can sensitize on different amounts of gas lift to distribute, or even if you're ever going to have some downtime and your supply goes down, how would you best distribute it? So there's been some operators who have really taken this very, very far, where every week they are getting the new conditions of the field in, they're running this, and they're sending the recommended gas lift rates out to the field to be applied. So the purpose of that is to keep all the wells basically in the sweet spot for their gas lift rates. So that, you don't have to, doing this once a year is probably not enough, but there are operators who are doing this literally every week to keep the wells in the sweet spot. And we're even doing an ERTEC paper with Devin about it. So this is really cool, but again, I'd recommend getting comfortable with the single well gas lift curve before you kind of dive into this. But it's really powerful, as you can imagine. I'm sure you're probably doing this in maybe like a manual way right now, but it's something, it's kind of like the advanced way to take advantage of all this gas lift stuff. So let me just wrap up with kind of what's coming around the corner. oh, I guess maybe to the point of someone who asked it in the chat is, can you make a gas lift curve reflecting different casing pressures? And really what that is saying is, what would the gas lift curve look like injecting a different valve depths? Okay, because if you change the casing pressure in Whitson, it's going to basically trigger a different gas lift valve that you've mentioned. If you put the gas valve depths and PSO, PSEs in, changing the casing pressure will trigger a different valve depth. And so the black curve is if we're injecting at the top valve, meaning, we can only go from where we are now up to the peak of this curve because we're injecting at quite a shallow valve. If we were to go down to a lower valve, we open up this new gas lift curve, lower valve, and lower valve. So really there's two ways to kind of skin the cat. If you want to increase your oil production, you can either increase your gas lift rate going to the right, following the curve. That's more gas lift. Or you can try to get to a deeper valve, which is ultimately reducing the density of the fluid at a deeper depth, right? One thing too, I'll just mention about gas lift curves. Wells that have very low reservoir GOR, they benefit more from gas lift. Wells that have a high reservoir GOR, they don't benefit as much from gas lift because that reservoir gas with a high GOR, it's acting like a natural gas lift. So, the black curve here is basically like a dead oil. And if we add gas lift, it's going to have a real benefit. It's going to have a real rate response when there's a very low GOR. But on the top curve, if you have a high GOR, like a naturally high GOR reservoir, it has less response to gas lift. So just a quick kind of intuition thing that you probably know, but it's nice to visualize that. I will quickly mention over injecting. This is a real thing that happens a lot. So this is a well that was producing 800 barrels a day. Now it's down to 200 barrels a day. This is a real case. And the reservoir gas rate was quite high, almost 5 million a day. And they were also injecting a lot of gas lift, like 700 to 1 million cubic feet a day of gas lift. This is how the well's operating. And so maybe you're thinking, okay, well, they're doing that to avoid liquid loading. But in fact, the well was not liquid loaded. There was in fact enough reservoir gas alone to keep it above the critical lift rate. And then if you add gas lift on top of that, you're way above the critical lift rate. So liquid loading was not a problem for this well at all. So if we look at the well, in the IPR VLP case, it's not liquid loaded, right? We're way over here. We're far away from liquid loading. So the gas lift curve for this well, this is what it looked like. The peak of this curve is right here, about 200,000 scuffs a day for gas lift. Where were they actually operating? They're operating way over here. So anytime you see that the current operating point is to the right of the peak, that's over injecting. Now, what if they turn gas lift off completely? Well, all we have to do is follow this all the way down to zero gas lift. The rate would be effectively the same. So just to give you a sense of the scale, I had to zoom in. Like this line is actually really flat, but I zoomed in. So 193 barrels, 194 barrels. So we're talking about 1 barrel a day here. And so by turning off gas lift, we predicted they would see no loss in production rate. Okay. So this was happening on a course. And so the operator actually went ahead and turned gas lift off a couple of days later in the field. So while gas lift was happening, this is what was happening during gas lift, and they turned gas lift off. What did the oil rate do? It actually temporarily went up and then stabilized at the same rate it was with gas lift. So, we had this diagnostic that said the well wouldn't suffer if gas lift was turned off. They tried it, and it happened that way. So this gas that they were injecting, they could instead sell it down the pipeline, or they could send it to another well that maybe needed gas lift. And then the gas rate also temporarily doubled because all that gas that they were injecting was just adding friction. That was all it was doing, is just making friction. And so the gas rate eventually stabilized back down to where it was before with the gas lift off. So anyway, this is just a real case of over injecting gas lift, and it's pretty easy to diagnose, kind of as I showed you, right? Now, just to to take the pressure off. How does this happen? How do people let over injecting occur? Well, it's because initially the GOR from the reservoir might be low. And when it's low, you need gas lift. But as the reservoir GOR naturally rises through the well's life, the need for that gas lift becomes less and less. And so if you haven't looked at the gas lift on your wells in a little while, it might be worth checking it out to see if it's even really needed anymore. Okay, it depends on the well, but especially if GORs are rising, you may need less gas lift. Okay, so you know what's coming. It really has to do with the future of the well. So what I'm talking about is, you know, when we do an IPR now, it's really just a moment in time, right? The IPR is changing for two reasons. Depletion, like the reservoir pressure is getting lower. But the second reason is with these unconventional wells, the productivity of the well is changing too. So the shape of the IPR changes as well through transient flow in the reservoir. So two reasons, depletion and productivity changes. So we have two ways. We have one way that we're going to approach this that we're working on right now. And the hope from this is not only to make future IPRs, but to say, if I make a change in the well bore, how will the rate change not only today, but what will the cum benefit be in a month, in a year, to basically make a pressure sensitive forecast without the need for a complex reservoir model. So the approach we're taking is we're going to define the size of the reservoir tank. And you can either do it using like the flow material balance, or just put like the volumetric fluids in place, you know, through like, you know, volumetrics, drainage area, net pay, porosity. Okay, so we define the size of the tank. We say, how much oil or gas has been produced from the well so far? So we take the original fluids in place in black, we subtract how much cum we've produced so far, and that's going to tell us what the current reservoir pressure is. So that's step one. How do the well's productivity? Well, we do the same way that we do now. Like when we make an IPR, we say, what is the current rate? What's the current drawdown? And that gives us a snapshot of the IPR today. All right. So that's very similar. What we're going to do is we're going to take this tank, take the current rate that the well's operating at, and we're going to forecast the well's production for 1 month into the future at that rate. So after 1 month of forecast, we're going to say, okay, at that rate, how much oil or gas will we have removed from this tank with 1 month of production at that rate? And so we subtract that amount of production from the tank produced at this rate for a month, and we get a lower reservoir pressure that will be there next month. Okay, so this is like a material balance way to predict how the reservoir pressure will change at this rate. You'll notice that the rate will go from like a high rate down to a slightly lower rate because of this lowering reservoir pressure. So what this means is we're going to be able to make a forecast of the well's future production in time. But the cool thing is it'll be pressure sensitive. So if you decide to schedule a gas lift rate change or an ESP change or a wellhead pressure change, the forecast is going to respond with the new rate. So this is kind of a new thing. Like, you know, with IPRs, we're just looking at a moment in time. We're not doing forecasting. So we're working on this right now. So that handles the depletion part of the production optimization, but it doesn't handle the transient, right? I remember that I said that the shape of the IPR is also changing because we're in such low permeability. The productivity is changing, and that affects the shape of the IPR. So effectively what we're going to do is look at the well's historical productivity index and how that's been changing. And we're basically going to draw like an empirical line through that to try to predict future productivity of the well. And so when we couple this future productivity prediction with the material balance of how the pressure will deplete in the reservoir through time, when we couple these together, we can really account for both effects to how the IPR will change and also how the well's forecast will change, even at different drawdowns and things like that. So this is kind of the way people had to do this in the past is with a numerical reservoir model, which not everyone has. And so this is just an alternative way for people to do this more empirically, to automate it and still get some results and associate production changes, productivity changes, operational changes with time. So this is just something we're working on. I do want to really mention that we've covered so much today. I just want to say this is like an introduction. Definitely reach out through support using this little button in the top if you run into any little hiccups as you're trying to apply this. And if you want to go through this at your own pace a little bit more slowly again, there's a question mark up in the top right. Okay, the question mark. And in the question mark is the manual, but I want you to notice something called certification on the left side. There's something called Nodal under certification. And this is where you're going to go through all these steps that we just covered today, but it's through like animations. Literally every single step is covered that